forward here a little bit. I forgot to charge this last night, which is what I try to usually do. I just forgot. Okay, it's not like we haven't mentioned this periodic table before, but let me give you a little bit of background. It's really rather fascinating because where we're going to end up with today is a pretty dramatic look at how the position of the electrons around the nuclei of these elements is really particular and aligns with where you find it in the periodic table. However, the person who started developing the periodic table developed it before we even knew there were electrons. Okay, so wrap your mind around that. We're going to find out there's a very close correlation between electronic configuration and its position in the periodic table. And the periodic table was developed before we even coined those terms or even knew their electrons existed. Okay? So to me, that's a fascinating thing. So who are we talking about? So late 19th, early 20th century, well, actually it's the mid-1800s that Mendeleev, see if we got a picture of Mendeleev, around 1870. So that is mid-late 19th century. A Russian chemist. Julius Meyer, a German chemist, but the one you hear the most about is Mendeleev, Russian chemist. Now remember, J.J. Thomson is starting to postulate that there's such a thing as electrons just a little bit after this time. So what was Mendeleev doing? Here's Mendeleev. I'm pointing somewhere. I'm pointing there. Okay. Oh, Mark, could you turn this front lights on? Let's. I don't know if I can. I guess I can't make that any bigger. But that's Mendeleev's scratchings in his lab manual. He didn't have the periodic table laid out like this. At that point in time, he and other chemists around the world knew of about 60 elements. There are 92 naturally occurring elements. So there's a good 30 elements that hadn't even been discovered yet. But they knew about 60, and what Mendeleev started doing, he started listing them from the lightest, hydrogen. Helium wasn't discovered yet. So hydrogen, we went to lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. He's listing these. Sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine. He's got this list. And he's starting to look at it from the smallest or lightest atoms to heavier atoms. And he's looking at their properties. How do they behave? What do they do? How do they react? Are they powders? Are they metals? What are they? And what he started seeing is he went down through there and he said, you know, sodium kind of behaves like lithium. Sodium and lithium have some common characteristics. So rather than just keep it in a nice long list, he started laying them out there, and when he saw a reoccurring property or similarity, he put that underneath that element. And he started kind of categorizing them by their similarities. And he'd go along there and he'd, oh, sodium belongs over here, and magnesium is like beryllium, and oh, chlorine is a lot like fluorine. Oh, potassium is a lot like sodium, which is a lot like lithium. And he started getting these families or groups of elements in columns and laying it out in a table form. And why do we call it periodic table? Periodic reoccurrence of similar properties. These similar properties are periodically reoccurring, like an old typewriter. Anybody ever seen an old typewriter? You type along there, and you get to the end, and what do you have to do? You have to, ching, you got to run the whatever they called it, the carriage, back over and start typing again, and it would get to the end, and you go ching, and I used to type on an old typewriter. Kind of neat. The bell would ring when it got to the end. Go up to Fredericksburg, where you have all those antiques. Hunt for an antique typewriter and see. Put a piece of paper in there. So it goes ching, and that that lets you know that you got to swing it back to the beginning again. So that's what's happening. This thing goes along here, and ching, and we got to go back to the beginning again. Ching, periodic reoccurrence, and we come up with this periodic table. So the periodic law, the physical and chemical properties of the elements tend to recur in a systematic or periodic manner with increasing atomic numbers. So as you line them up by atomic number, systematically you'll see the reoccurrence of properties. So I've got a little video. I won't show it today, but someday I will try to show it. It's just really kind of dramatic. It's 3 or 4 minutes long, and it just shows you how similar those elements are. They're soft metals. You can take a knife and cut them. Lithium, sodium, potassium. You can take a chunk of potassium and cut it with a knife. You can take it and drop it in water, and it will react, spontaneously react with water and give off a gas, and that gas is flammable. So they all do that. They all do that. Some of them do it faster than others. Lithium is kind of slow. You can play around with lithium. Sodium is all right. Potassium, you can't even sit it out on the table very long. It'll start bubbling and foaming and reacting with the moisture in the air. It reacts with water very fast. And francium, well, cesium will explode. You take it out of the bottle, it'll start, or get it wet, drop some water on it, darn thing will explode. So it's very vigorous. Same reaction, but a little bit more vigorously. So that's just an example. You come over here, come over to the other side, and they're very different over here. These aren't metals. This is a gas, a liquid, a solid. They're diatomic molecules, F2, Cl2, Br2, I2. They are reactive and poisonous. They are not like those. Very different properties. Those are metals. These are non-metals. All right? So it's just a little flavor. So let's get our feet on the ground. What this... did I just write on that? Yeah, I did. Here's kind of the organization of it. All over here, these are, well, not that one. All of these are metals. Those are metals. So the vast majority of the elements on the periodic table are metals. This right here are your nonmetals. So those are nonmetals. These are the noble gases. These were some of the last elements discovered. They don't react with anything. They're present in the atmosphere in very, very small quantities. Amarillo, Texas has the world's largest supply of helium. Amarillo, Texas. Back in World War I, when dirigibles were kind of military interest. You know, we didn't have a lot of planes, and we had these helium dirigibles. Helium was considered a militarily important substance, and so they stockpiled it in Amarillo, and it's still up there. Some interesting thing I learned a little while ago. But these things don't react with anything, and so they were hard to discover, and so it wasn't even until like the 1920s that they're discovering the noble gases. 1910s, something like that. And then these are metalloids. See the boron, the silicon, the germanium, lead, antimony. The green ones there are metalloids. They can have metal or non-metal characteristics. Okay, let's get a few terms in mind. When we look at a row of elements on the periodic table, we call it a period. So hydrogen is in period number 1. Lithium begins period number 2. Sodium begins period number 3, that row. You can see there's just 7 of them. 7 periods. A column on the periodic table will be referred to as either a group or family. And some of them have very characteristic names. Group 1 is the alkali metals. And group 2 is the alkaline earth metals. So don't get those mixed up. Alkali metals, that's group 1, starting with lithium, sodium, down through there. And group 2, starting with beryllium, is the alkaline earth elements. I already mentioned over here, now I need to change these numbers. You will see these numbers, but you will also see it'll go from 1, 2, 3, 4, 5, 6, 7, and 8. And I don't know what they're doing with these numbers. I actually don't know what they're doing with these numbers. But the 1, 2, 3, 4, 5, 6, 7, and 8 are the main group elements. You'll see why as we move along into this. Main group elements. And the 8 over here are the noble gases or inert gases, and these are the halogens. Those are the 4 groups I want you to know the names of. So if the question were, what's the name of the group 1A elements? It's alkali metals. And it might be a multiple choice question. It might give you 5 choices, but the correct answer is alkali metals. Or it might be in the fill in the blank. Then what is the name of the group 8A elements? Noble gases. All right, these are the transition metals. So right in this, from what they got numbered here, 3 through 12, are the transition elements. All right, that's getting our feet on the ground a little bit, the makeup of the periodic table. You can see we got yellow, green, and blue, and different shades of blue on this up here. Up here we've got black, red, and blue. So what's this telling us? These colors are telling us what is a solid, a liquid, or a gas at room temperature. So all the black ones are solids at room temperature. The blue ones, and there's only 2 of them, mercury, this is kind of unusual, dug right down in here, this very, very heavy element, it's a liquid, room temperature. It's pretty amazing. Sitting right there next to gold, which is a solid, cadmium's a solid, and we got this mercury. Don't ask me why. That's a good question. It's a very good question. Why is mercury a liquid? Bromine's a liquid. And then the red ones are gases at room temperature. Hydrogen, nitrogen, oxygen, fluorine, chlorine, and then the noble gases. One semester, and you, yes?
What are the white ones?
Oh, the white ones, very good question. The white ones are man-made elements. They are synthetic or man-made elements, and in many cases, particularly when you get up to high numbers, they existed for a millisecond. They existed long enough to get some sort of a spectrum or print or image of it to show that it did exist. Matter of fact, I think these last four were discovered or created made from smaller atoms around January of this year, December last year or something, just in the past 12 months. So yeah, these are, so in high particle accelerators, they make these elements and they exist for different periods of time. They're very, very radioactively unstable. So is uranium. Uranium is a radioactive element. It's got 92 protons packed in a little nucleus. But then you start getting up to 100, 116, 118, it's just unstable. They exist and then they decay very quickly. Good question. Okay, there's just another view of Dmitry Mendeleev, and I don't know exactly how they got a photograph of him back in 1870, 1880, 1890. I don't know. I guess yeah. They got a picture of Abraham Lincoln giving the Gettysburg Address. They almost did. The cameraman was taking a long time getting set up, and he talked too fast. He sat down. He said, "Wait a minute, I'm here to get a picture for the New York Times. Go back up there." Something like that. Oh well. That's history class. All right, there's some slides. All right, we already talked about this. What you've got there. You've got the symbol. You have the name of the element. I thought I could make these things bigger, but I apparently can't. You got the atomic number. So hydrogen is number 1. And you have the atomic mass. And on your periodic table, we have it as rounded off to 1.01. All right, there's another kind of look at it. You can see here's the names I'm talking about. Those are the 4. You don't need to learn. That body right there, that's the transition metals. And then you got the lanthanide and the actinide series. And you're going to see from electronic configuration what this is. So let's try to start laying the groundwork. Metals. What you want to do is learn this. Metals, they tend to lose electrons and form positive ions, and as we learned this morning, those are cations. A positive ion is a cation. Nonmetals tend to gain electrons and form negative ions or anions. All right? Those are a couple worthwhile things to keep in mind. This is what's happening. In chemistry, what is happening is electrons. It's got to do with what the electrons are doing and why they are doing it. Will tell you a lot about the chemistry of an element. So that's why we have to learn this. If we learn the electronic configuration and we understand why something will lose an electron or why it would have the tendency to gain an electron, we can start predicting its chemical behavior and other behavior, other properties. Okay, there's that symbol. All right, so let's get back to Bohr. This is combining now the Bohr atom and Schrödinger and Heisenberg's quantum mechanics that got into a finer detail of the Bohr atom. So let's see. Remember the spectra? We talked about fireworks. We talked about neon lights. The emission spectra. From the emission spectra, Bohr postulated that we got this image of the atom now. We got a nucleus where we have protons and neutrons at the center of the atom. Positive charges here. And what's out here in this space around the nucleus? Electrons. And so then, in the early 1900s, then Bohr, Heisenberg, Schrödinger, everybody was thinking about, okay, what exactly are those electrons doing out there? Where are they? And that's where we're at right now. So Bohr said, number one, that the electrons go into principal energy levels. So N1, don't get bogged down in all these lines right here for right now. Just think there's the principal energy level number one, and there are actually 2 electrons that could fit in there. You can see that's close to the nucleus. It's small. It's a small energy level, close to the nucleus. Can't get a lot of electrons there. Number 2, principal energy level number 2 is a little further out. It's higher energy. It's further out, so it's bigger. It can hold more electrons. Number 3, bigger yet, can hold more electrons. Number 4, bigger yet. And there's only going to be 7 of these. So 4, 5, 6, and 7 energy levels. If you went all the way up to uranium, you could fit all of uranium's 92 electrons in those 7 energy levels. Okay, now Schrödinger and Heisenberg, Bohr's view of it was very specific. It was like they were in orbits around that nucleus. Schrödinger and Heisenberg came in and said, you know, those electrons are a little bit more flexible than that. They're not just spinning around in this orbit like the Earth is going around the sun. They are actually going all over the place, but there's a certain place that they're most probably going to be. And that Heisenberg's uncertainty principle got into what is the area of highest probability of finding those electrons. And that's when they started talking about orbitals. They did not blow Bohr's energy levels out of the water. So you have energy levels. And then within energy levels, there are orbitals. Hang on a second. I'm going too fast. The energy levels, there are sub-levels. And then within the sub-levels, there are orbitals. And orbitals get only 2 electrons. And then in here, the electrons can have a spin. They can be spinning clockwise or counterclockwise. So these 4 things, what energy level it's in, what sub-level it's in, what orbital is it in, and what direction is it spinning, is a unique electron. No electron that will have all of that stuff. So let's get down to this level right here. So energy levels, 1, 2, 3, up to 7. Sublevels, S, P, D, and F sublevels. It's probably good enough for us to just sit right here for a little bit. Energy levels and the sublevels. So if n equals 1, sublevels. Remember, I told you as you go further out, these energy levels get bigger. They can accommodate more electrons. So the very first one can only accommodate 2 electrons, and it only has an S sublevel. So that's what you got right here. I just might need my... Oh, I know what I got my high-tech pointer. Get out my high-tech pointer. I was going to use the... All right, so that's what we got right there. We got 1 energy level. The n equals 1 energy level can only have S sublevel, can only hold 2 electrons. So you get down to the second energy level. It has an S sublevel with 2 electrons in it, but in addition to that S sublevel, there is a P sublevel that holds 6 electrons. So 2 plus 6, you can get 8 electrons around here in the second energy level. Okay, I know I'm going to throw a lot at you at once, and then we're going to assimilate it and start using it and getting it down. So there'll be some things to help you, like this. Third energy level. It has an S sublevel with 2 electrons in it. It has a P sublevel with 6 electrons in it. And in addition, it has a D sublevel with 10 electrons in it. 2 and 6 is 8, and 10 is 18 electrons. So this has a total 2 electrons, 8 electrons, 18 electrons. You with me? All right, and then you get down to the fourth energy level, and it has all 4 of those sublevels. S, 2 electrons. P, 6 electrons. D, 10 electrons. F, 14 electrons. And that's 32 electrons. Add 14 to this number, and you get 32 electrons out of it. Now remember, I told you this continues on. Oh, I left out 5. 5, 6, and 7. But there are no more sublevels. All right, it would still be those same sublevels. Okay, now, and let me share something with you in a second. So the S, P, D, and F, maximum number of electrons. How many can the S hold? 2. How many can the P hold? 6. How many can the D hold? 10. And F? 14. Okay? Now if you want to, and this I got from a student, this was about 4 years ago. So, please don't forget. So please don't forget that they go in that order, and they go by this size. This is their capacity. Okay, you drove here in a vehicle this morning, or you got a ride via bus this morning with a certain capacity. Whether there was that many people in the car with you or not isn't what I'm talking about. I'm talking about how many can it hold. All right, your car came here, holds 5 people, but you may come all by yourself. There's only one of you in that 5-vehicle car. So we'll be talking about how many electrons are in certain places. Now so I'll leave some of this on the board so we got energy levels, sublevels. We'll talk about orbital diagrams here in a minute. I want to get to the electron configurations. We'll look at some orbital diagrams. Can I erase this? One other thing to keep in mind, is that electrons go into the lowest energy level available. All right? Closer to the nucleus is lower energy. These are higher energy levels. So when we say higher numbers, they're also higher energy. It's like water. You pour water somewhere, and what happens? It flows to the lowest level it can get to, right? Gravity pulls it down to the lowest level. So you pour something out on this table, it's going to drip off onto the floor. It's going to naturally go to the lowest energy level it can go to. That's the same with electrons. You bring an electron in to something. Now, Mark, you can turn this light back on, please. You'd bring an electron into this diagram right here, and it's going to go, and I'm going to give you some examples right now, and then I'm going to give you an activity to do, and we're going to be putting it up on the board before we get here so that we can work on these electron configurations. I'll give you an activity in just a second. But let's walk across here. Hydrogen, helium, lithium. Let's walk. We won't do everything, but we'll kind of walk over to fluorine, do a few examples. And I'm going to work off of this symbol. Now remember our symbol here, we had a Z number and an A number here. I'm going to focus on this atomic number. We're not talking about isotopes. We're talking about protons and electrons. Now what do we know about, so hydrogen has an atomic number of 1, and if there is no charge there, so this has 1 proton, how many electrons does it have? 1. If there is no charge, in other words, we're talking about a neutral atom, the number of protons equals the number of electrons. Has to. Protons are positive. Positive 1 for every proton, negative 1 for every electron. So for it to balance out to be totally neutral, there has to be an equal number of them. So I'm going to just write this symbol right there. It tells us, now I'm going to write it a little bit smaller because I want to make a little list of these. I'm going to keep that in mind. So we got 1 electron. Where is that electron going to be? What energy level? First energy level. What sublevel? S. That's the only sublevel the first energy level has. So we give it an electron configuration. 1, that's the energy level, the sublevel, and that's how many electrons are in it. So the electronic configuration of hydrogen is 1s1. That's its electronic configuration. Helium. I'm getting that number right off the periodic table. Atomic number. It has how many electrons? 2. Where are they? What energy level? 1. And they're in what sublevel? S. And how many are in there? 2. It holds 2. You can hold 2. So it doesn't go to the second energy level. Not yet. That's helium's electronic configuration. So then let's go over to lithium. It's got 3 electrons. Oh, I'll tell you what. Let's get one other chart up here. Here's where Heisenberg, a little digression. Here's where Heisenberg and Schrödinger came in. They said, hey, you know, these orbitals, and this is Schrödinger's equation. I mean, if you take about 4, 5, 6 more math courses, you can start thinking about Schrödinger's equation. And I mean, don't think I'm an expert on Schrödinger's equation. This is quantum mechanics. This is very high-level math and physics. But Schrödinger and Schrödinger's equation stipulated where's the probability of finding these things. And this is all coming off of the hydrogen atom. You can only do this math on a very, very simple atom, helium, or hydrogen, 1 electron. So this is what it would look like. So they're spherical orbitals, but they get bigger. And then the p orbitals. There are 3 of them, and that's why it holds 6 electrons. Each one of these orbitals holds 2 electrons. 2, 4, 6. That's your p orbital. Put p sublevel. Your d sublevel has 1, 2, 3, 4, 5 orbitals. So don't get bogged down in that. That's just to get you to the orbital level. And then there is a slide coming up here. All right, here's the important one. What I said is the first energy level is the lowest energy level. So for hydrogen, I would say, I got an electron right there. For helium, I got another electron right there. And I do arrows pointing in opposite directions. They're spinning in opposite directions. That's how they tolerate each other in the same orbital. They spin in opposite directions. And then we'll move on up from here. Second energy level. 2s is the lowest orbital, so the electrons go into 2s first, and then they start populating 2p, 3s, 3p. But now look very carefully at 3d and 4s. Which one's lower energy? Here's your energy scale. Which one's lower? Well, 3D should be. I mean, that's what we think. The third energy level should be a lower energy level. But that is lower than 3D, 4S. So what that tells us is that the 4S orbital starts filling before the third energy level is full. It gets 3S filled, it gets 3P filled, and then there is a pause in filling the third energy level until you get 2 electrons in the 4s. And then you pick up finishing off the 3D. So this is a little sticky wicket. This messes things up a little bit. So take your periodic table. Can I borrow yours for a second? This chart is what you have to start learning how to use. Let's go down here a little bit more. Lithium. Lithium has 3 electrons in it. So 1, 2, and where's the next one going to go? Right there. So it has a 1s2, 2s1 configuration. And then we have beryllium. Where's that electron going to go? Right there. There's still room right there. And And that is your lowest energy orbital that it can go into, or sublevel it can go into. So it's going to be 1s2, 2s2. Now let's do oxygen, and then we'll do fluorine. 8. So let's start all over with oxygen. Oxygen has how many electrons? 8. 1, 2, 3, 4. There's 3 orbitals right there. They're all of equal energy. 5, 6, 7. So the electrons are going to go in, one is going to go into each one of them because they have space there. And then they're going to carpool. See, we don't carpool until we have to. So the 8th one goes in there. So how would I write that one? Well, I'm going to say it's a 1s2, a 2s2, and then this baby right here, I'm going to write as 2p4. I'm going to take that whole sublevel that has 3 orbitals in it. I'm going to bunch it all together as the p sublevel, and it contains 4 electrons. Now let's jump up to a really high one here. Something that's going to, like iron. Let's do iron real quickly, and then I'll give you this sheet when we have enough time to do this. 26. So let's just do this. Can I move this down at all? Can't. I'm not going to be able to reach up there. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, now here's the rub. We've got the 3p. The next thing is 4s. What did I say that was? 18? 19, 20, and then I'm going to get 6 of them in there. We can do this. How do we do this? That. So we need 6 more. Oh, we can't do it. 1, 2, 3, 4, 5, 6. Who's real tall? Got someone tall? There's a marker right there. 1, 2, 3, 4, 5, 6. So what would that look like? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And then 3d6. And then notice one other thing. Here, look at this number here, 26. Look at these numbers. 2 plus 2 is 4, plus 6 is 10, 12, 18, 26. You add up all those numbers, and it equals the atomic number. We're starting out here saying there are 26 iron atoms here. There are 26 protons here. There's 26 electrons in the iron atom. Okay, I'm not going to. We'll do this exercise first thing Thursday morning. Let's dust off a couple of concepts here so you start getting familiar with electronic configuration. And let me show you what we just did here. Now notice this. So what did we do? We filled the 1s and then we filled the 2s, and then we filled the 2p and the 3s and the 3p. But rather than move over here to the 3D, we went to the 4s. That's how this chart is helping you. And then we came back here and we did some into the 3D. That's what we did for iron. To do the iron 26, that is the flow pattern we went with. So what are we saying? Don't just fill an energy level indiscriminately. Don't just fill the entire third energy level and then start the fourth energy level and fill it, and start the fifth energy level and fill it. You won't get the right electronic configuration. Yeah, we'll come back to the correlation with the... So that is there. You don't have to memorize that chart, but you have to know how to use it. What else you need to know? You need to know that this holds 2 electrons, that this holds 6 electrons, that this holds 10 electrons, and the F holds 14 electrons, no matter what level you're talking about. And when I write 1s, I'm talking about the s sublevel in the first energy level. And if I write 5s, I'm talking about the s sublevel in the fifth energy level. All right, that first number is energy level. Second thing is the sublevel, and then the number of electrons in it is put there as, I won't call that an exponent, as a superscript. Okay, now, this isn't moving. Okay. Would you ever see something like this? Would you ever see a 4s3? No. No, you won't ever see a 4s3. So don't put 3 electrons into an s sublevel. You won't ever see a 5p7. Don't you say, I got 7 more electrons, I'm going to put them in the p sublevel. They won't fit there. It only holds 6 electrons. Okay? So if you are armed with this chart, with this knowledge, and with the knowledge that electrons go into the lowest energy level first and then fill from there, you can get the electronic configuration of anything, any one of these elements. I tell my classes, if you were on a New York subway and someone said, I'll give you $1,000 if you can write me out the electronic configuration of uranium, you could say, okay, I'm on, I can do that. I know this chart, I know this, and off you go. And you can fit 92 electrons in there. Okay? Okay, you've got, I don't want to start this activity and not be able to finish it, so we will do it on Thursday, and it will solidify some of this and show how electronic configuration correlates with the periodic table.